let's discuss the squeeze theorem. I'm going to first explain it to you in a way that you will have no chance of understanding, and then I'll bring it into terms you're going to understand. This is going to be wonderful. Let L be an interval having the point A as a limit point. So in other words, we have x approaching A. Let G, F, and H be functions defined on this interval, except possibly at A itself. Suppose that for every x in L not equal to A, we have this dynamic. Now this dynamic is saying that any place on the function H is always the biggest, G is the smallest, and F is in the middle. In a sense, H and G are squeezing together for F. I was once asked, do you want an XL or do you want to squeeze into an L? And also suppose that the limit of g of x as x approaches A equals the limit of h of x as x approaches A, and those both equal the same thing, L. Our conclusion is the function f, the one in the middle, as x approaches A, also approaches L. I know what you're thinking. That didn't make any sense whatsoever. Let me try to illustrate, and then I'll put in terms that you'll understand. Hopefully. Let's say that this is just some random function, which we'll call h. It's the upper bound here. And let's say this is some function, g. It's the lower function. And then let's say that we have a function f, the middle one, that no matter where we graph f, it never goes below the blue curve and it never goes above the purple curve. It just keeps going back and forth, never above h, never below g, and it continues like that forever. Now, with that being said, if I were to choose, let's say, what's the limit of h of x as x approaches, let's say, the number 4. And let's say that 4 on this graph correlates to 10, and 4 on this lower graph correlates to negative 10. So let's say that if we evaluate this limit and we get 10, and then we evaluate the limit of this lower curve at 4 and we get negative 10. Now that doesn't tell us what the limit is of f of x at 4, but it does seem reasonable to think that whatever that limit is, it has to be between these two y values, because the graph's always between it. So in other words, the limit of h of x as x approaches 4, which we know is 10, has to be less than or equal to the limit of f of x as x approaches 4, which is less than or equal to the limit of g of x as x approaches 4. Once again, we're saying this is true because g is always the upper curve, h is always the lower curve, and they are squeezing together this function in the middle, which is f of x. So if this, I wrote this backwards. Blimey. Pardon me. So if h of x is approaching 10, and g of x is approaching negative 10, then it seems reasonable to assume that this limit here of the function between has to be approaching a number between negative 10 and 10. In essence, that's the squeeze theorem. Now, in its current form, with this example, that was not very valuable, but I'll give you another example here that's more valuable. Before I do that, let me put this in terms that you will definitely understand from Wikipedia. In many languages, examples French, German, and Italian, Hungarian, and Russian, let's focus on the Hungarian, the squeeze theorem is also known as the two policemen and a drunk theorem. This is good. Or some variation thereof. Citation needed. The story is that if two policemen are escorting a drunk prisoner between them, so let's do that. Boy in blue right here. And his twin brother. They are escorting a drunk between them. Those are suds. And blah, 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 escorting a drunk prisoner between them, and both officers go into a cell. Then, regardless of the path taken and the fact that the prisoner is wobbling about between them, so this prisoner is kind of, you know, he's always between these two. Doesn't matter where they go. If we have a jail cell over yonder, if both of the police officers get inside the jail cell, then the drunk has to be in there as well, because he's always between where they are. The two policemen and a drunk theorem. We were trying to find this limit. The limit as x approaches 0 of x squared times sine of 1 over x. If we try to use direct substitution, this is going to be 1 over 0, which is undefined. So how are we going to do this? Well, first of all, let me show you what this graph looks like. So this is that graph, and it looks like it's linear to some degree, but if you examine this a little bit closer, let me change my window a little bit. You can see that this thing starts moving up and down and oscillating in here. So what we need to figure out is, how do we find a function that's always above this and another function that's always below it? Two police officers escorting this drunk. Here's what we're going to do. We're going to, first, I want to remind you that y equals sine of x, where x is just some angle. That is a graph. It starts at 0, 0, goes up and down forever as it goes left and right. High as it gets is 1, low as it gets is -1. Now, it doesn't matter what this angle is. That's always going to be the case. If we manipulate this angle, it's going to change things happening horizontally, but it's not going to affect the graph vertically. Things that affect it vertically happen on the outside of the function, like if we're multiplying by a number here, or if we're adding or subtracting a number out here. So with that being said, since 1 over x is just an angle, just like this is an angle, sine of 1 over x has to always be less than or equal to 1, and it has to always be greater than or equal to -1. Because the graph of sine of x never goes above 1 or below -1, and x is an angle, and this is just some angle. It affects the graph horizontally when you change it, doesn't affect it vertically. This graph is always between -1 and 1. Now, once you've established, and this doesn't always, you can't just pick random things for this to work with. Like, these problems are specific and difficult, and I'm telling you it's going to be between -1 and 1, and hopefully it makes sense to you once I've said that. We want to manipulate this inequality so that we have an x squared times sine of 1 over x in it. We currently don't have an x squared. Using algebra properties, we can multiply every term by an x squared. So I'm going to multiply this by x squared, this by x squared, and this by x squared. If I do that, I get -x squared less than or equal to x squared sine of 1 over x less than or equal to x squared. Now we are cooking. And let me show you what this looks like. If we were to graph this function and this function and this function, are these in fact the two police officers escorting this drunk into a cell? I'm going to turn on the x squared and the -x squared. And if you look at this, I'm going to get closer. Notice how the black curve, the drunk, is always going between the two police officers, the top curve and the bottom curve. it doesn't matter how far out we go or how far in we get. This is pretty cool if you keep going in. Isn't that awesome? Doesn't matter how close we get or how far away we get. This black curve is always between those two. So at this point, let's try to find the limit of each of these and see what happens. So on the left, if we find the limit of a negative x squared as x approaches 0, in the middle, we don't know how to find this limit. If we did, we wouldn't be using the squeeze theorem. And on the right, we have the limit of x squared as x approaches 0. Now we can figure this out pretty easily. If we substitute a 0 in for this, we're going to get 0 squared, and it's a negative 0 squared, which is 0. Don't know how to figure this out, so I'm just going to bring that down. Over here on the right, as x approaches 0, x squared is going to also approach 0, because if you put 0 in for this, 0 squared is 0. And here's the beauty of the squeeze theorem. The two police officers escorting a drunk theorem. Since this is being squeezed together, this limit that we're trying to find in the middle has to be less than or equal to 0, but greater than or equal to 0. There's only one number that exists that's less than or equal to 0 and greater than or equal to 0, and that number is 0. Therefore, the limit as x approaches 0 of x squared times sine of 1 over x is 0. Now here's the nice thing about the squeeze theorem. You won't need it on the AP test. In all the years that the AP test has existed, they have only asked about the squeeze theorem one time, and they didn't call it by name. It was a problem that could have been done by the squeeze theorem. And that was last year, that's true. But the results on the test, the students' performance on that were terrible. It is highly unlikely that they're going to ask you about the squeeze theorem on this test. And if they do, I can almost assure you that you could figure out the answer using a different method than the squeeze theorem. So there's an example, there's a formal definition, and the two officers and a drunk theorem. Hopefully that made some sense to you.